Alright, so this is group B37 talking about permutations with indistinguishable objects and the multinomial theorem. This is Ashley, Dominic, Jacob, Jason, and Sherwin. And this video will be featured on knoatom.com. And for more videos about discrete mathematics, you can go ahead and visit that website.
Alright, so we're going to start with example 1. We're going to try to find the number of permutations of the word Mississippi. Now you see there's a lot of letters that repeat itself in Mississippi. First we're going to find the total number of letters, not counting repeats. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. Alright, now we're going to find the number of S's, because S repeats through the word. There's 4 of them. We're going to find the number of I's. There's also 4 I's. And the last letter that repeats are the P's, and there are 2 of those. All of the other letters, well, the only other letter, M, only occurs once through this word. So first, let's find the number of different ways that we can place S in our mixed up version of Mississippi. To do this, we do C, a combination of the total number of spots available, which we found to be 11, then the number of S's that we have, which is 4. And this is going to leave us with 11 minus 4, or 7 more spots to place the remaining letters. So we have 11 factorial divided by 4 factorial times 7 factorial. Now we're going to find the number of ways that we can place the I. This is going to be very similar, except now instead of 11 spots, we only have 7 spots to place the I. But we still have 4 I's. So this is going to be the combination of 7 objects choosing 4. We have 7 factorial over 4 factorial. And this is going to give us a remainder of 3 characters, or 3 places, to choose for the remaining letters. Now we're going to find out where we can place our P's. So we're taking the combination. We now only have 3 spots left, and we have 2 P's. So we're taking the combination of 3, choose 2. This is going to be 3 factorial divided by 2 factorial times 1 factorial, because there's only 1 spot left. And now to place the M, there's only 1 M left, so it's going to go in the last spot, the last remaining spot, which is the combination 1 choose 1, which is obviously going to give us 1. Now to find out the total number of permutations, we have to multiply all of these numbers together. This is going to give us 11 factorial times 7 factorial times 3 factorial, and this divided by 4 factorial times 7 factorial times 4 factorial times 3 factorial times 2 factorial times 1 factorial, which is going to give us 1. Now you will see that the 7 factorial cancels out of both the numerator and the denominator. I'll take that out. And we know that this 3 factorial is going to cancel out with the with this 3 factorial. And we now are left with 11 factorial over 4 factorial times 4 factorial times 2 factorial. So taking 11 factorial divided by 4 factorial times 4 factorial times 2 factorial, we get 34,650 different combinations of the letters within the word Mississippi.
Okay, would be the following. N factorial divided by n sub 1 factorial times n sub 2 factorial all the way to n sub k factorial.
Alright, so now we're going to go ahead and prove this theorem. So to determine the number of total permutations, we first have to note that the n1 objects of the first type, like in our example, the four objects of type S, can be placed among the n total positions in whatever you have in n choose n1 ways, which leaves n minus n1 total positions that are free after this. So then the objects of type 2 can be placed in n minus n sub 1 choose n sub 2, which leaves us with n minus n sub 1 minus n sub 2 positions open. And we're going to keep going on. We can keep going on like this for the objects of type 3 all the way to the objects of type k minus 1. And then at the last stage where we have n sub k, or the n sub kth object type of type k can be placed in choose or n minus n sub 1 minus n sub 2 minus ... all the way to n sub k minus 1 minus n sub k, or sorry, that choose n sub k. So this is the total number of permutations for the last object, or the last n sub k objects. So then we have all these different possible permutations for all the different objects of type 1 and type 2 all the way up to type k. And by the product rule, the number of different total permutations is here n choose n sub 1 times n minus n sub 1 choose n sub 2 times ... all the way to n minus n sub 1 minus n sub 2 minus ... minus n sub k minus 1 choose n sub k. And this equals n factorial divided by n sub 1 factorial times n minus n sub 1 factorial times n minus n sub 1 factorial divided by n sub 2 factorial times n minus n sub 1 minus n sub 2 factorial all times ... times all the way up to n minus n sub 1 minus ... minus n sub k minus 1 factorial divided by n sub k factorial times 0 factorial. And this, if we cancel out, we can cancel out like here this n minus n sub 1 factorial with this one up here, and then this one with the next one, and 0 factorial is just 1, so that doesn't matter. And we'll end up with n factorial divided by n sub 1 factorial times n sub 2 factorial all the way up to n sub k factorial. And this right here was the multinomial theorem, which we hypothesized up here.